A man in a white suit kneels in the grey dust of the moon. He picks up a rock. He has no idea that he is holding one of the strangest objects in the solar system. It is small, dark grey, heavier in the hand than it looks. He carries it 250,000 miles back to Earth, where it is catalogued, photographed against a centimeter ruler, and sealed inside a clean room in Texas. And there it sits beside 1,000 other moon rocks. Then someone slides it next to an instrument that measures magnetism. The needle climbs. It goes past where the physics says it should ever be able to go, because this rock remembers something. When it formed, deep in the moon's past, it cooled inside a magnetic field, and it froze a record of that field into itself, like a photograph taken in stone. Read that photograph today, and it tells you something that should not be possible. When this rock was born, the moon was wrapped in a magnetic field stronger than the one around the Earth right now. That is the thing that shouldn't be there. By every rule we understand about how worlds make magnetism, the moon should never have been able to do this. And yet the proof had been in our hands the whole time, gathered by the astronauts. To understand why that rock was so disturbing, you need to understand how a world makes a magnetic field in the first place. Planets and moons generate magnetism from their cores. Deep inside, where it's hot enough to keep iron molten, that liquid metal churns and circulates in great, slow currents. Moving metal makes electric currents. Electric currents make magnetic fields. We call this engine a dynamo, and it's the same machine that wraps the Earth in the invisible magnetic shield we live inside every day. Here is the rule that comes out of that. The bigger the churning core, the stronger the dynamo, the stronger the field. A big core can power a big magnet. A small core can only manage a weak one. And the moon's core is small, genuinely small. It's only about 1/7 of the moon's radius. By the logic of the dynamo, a core that size should produce a faint magnetic field at best, or none at all. So when scientists measured the Apollo rocks, they expected the numbers to be quiet, modest, maybe even 0. Instead, some of those samples recorded a magnetic field strength that, in places, may have exceeded 100 microtesla. Let me let that sit for a second, because this is the single strangest fact in the entire story. The magnetic field at the surface of the Earth, the field that turns every compass on the planet, the field generated by our enormous, roiling iron core, is typically around 40 microtesla. The Apollo rocks were pointing to a moon that, at moments in its past, had been wrapped in a field more than twice that strong. A tiny world, with a core barely a fraction of its size, somehow producing a magnetic field that outmuscled the Earth's. One of the researchers who would later untangle this described the problem in a way that sticks with you. She said it was as if an AA battery were somehow powering a fridge. The energy source is far too small for the result it's producing. The numbers simply don't balance. And this wasn't one freak rock. This pattern showed up again and again in the Apollo collection. Roughly half of the relevant samples carried this fingerprint of intense, impossible magnetism. So scientists were left holding a contradiction. On one side, hard physical evidence, frozen into real rocks, that the moon once had a ferociously strong magnetic field. On the other side, everything we understood about how small cores work, insisting that it was impossible. For decades, the field split into two camps. One camp looked at the rocks and said, the moon must have had a powerful, long-lived magnetic field, and our physics is missing something. The other camp looked at the physics and said, the moon's core is too small, the field must always have been weak, and there's something we're misreading about the rocks. Both sides were certain, and the argument ran on, year after year, while the rocks sat quietly in their vault, holding the answer the whole time. That makes sense as a stalemate. Two solid pieces of evidence pointing in opposite directions and no way to choose between them. But a stalemate isn't an answer. And the answer, when it finally came, wasn't going to declare one side the winner. It was going to do something stranger. It was going to prove that both sides were right. The break came from a planetary geologist named Claire Nichols, working with colleagues in the Department of Earth Sciences at the University of Oxford. Nichols had spent a long time staring at this contradiction. The magnetism in the Apollo rocks didn't fit the physics she trusted, and that bothered her in the specific way that a wrong number bothers a scientist, like a single note played off-key in an otherwise perfect chord. As she put it, it simply doesn't make any sense with the physics we understand about how planets generate magnetic fields. For years, modelers had been trying to force the moon's tiny core to produce these enormous fields. They invented mechanism after mechanism, exotic ways to supercharge a dynamo that should have been incapable of it. Nothing quite worked. The AA battery still refused to power the fridge. And then one of her Oxford colleagues, a petrologist named John Wade, a scientist who studies what rocks are actually made of, said something almost in passing. Wade asked, more or less as a throwaway comment, whether anyone had ever checked for a link between the composition of these rocks and the intensity of their magnetism. In other words, stop looking only at how strong the magnetism is. Start looking at what these rocks are made of, and see if the two things move together. Nichols went back to the data, and when she lined it up, the pattern was almost too clean to believe. Every lunar sample that recorded a strong magnetic field also contained large amounts of titanium, and every sample with only a little titanium, anything below about 6% titanium by weight, recorded a weak field. The magnetism and the titanium rose and fell together. The strongest magnets were the most titanium-rich rocks. The weakest were the titanium-poor ones. There were no real exceptions. She later called it a proper eureka moment. After decades of an argument that wouldn't move, the key turned out not to be in the physics of the core at all. It was in the chemistry of the rocks. It had been hiding in plain sight in the Apollo samples the entire time, waiting for someone to ask the right question. But a correlation isn't an explanation. Knowing that titanium and magnetism travel together doesn't tell you why. To answer that, the Oxford team had to follow the titanium all the way down through the crust, down through the mantle, down to the boundary where the rock meets the core. And to do that, we have to go back even further than Apollo. We have to go back to when the moon was an ocean of fire. When the moon first formed, it was not a world of grey dust and silence. It was molten, an entire globe of liquid rock, glowing, churning, with no solid ground anywhere, what scientists now call the lunar magma ocean. This stage happened very early, somewhere around 4.5 to 4 3/10 billion years ago, during the moon's initial formation. We know this ocean was real because the Apollo rocks told us so. Among the samples, scientists found fragments of a pale, light-colored rock called anorthosite, a rock made almost entirely of a single mineral. So pure, it's genuinely rare to find anything like it on Earth. The way you make a rock like that is to let it crystallize and float, like an iceberg, on the surface of a molten sea. The anorthosite in the Apollo collection is, in effect, the frozen scum of that ancient ocean of fire. It was one of the first great discoveries the samples handed us. Apollo 11 only carried small fragments of it, tucked inside those breccias. The later crews went looking on purpose. Apollo 15 and Apollo 16 were trained to hunt for it and brought home larger, cleaner pieces of those pale highland rocks, the floating crust of the magma ocean, sampled directly. It's worth pausing on how the idea even arrived. The magma ocean was first pieced together from the chemistry of the Apollo 11 samples, though the phrase itself wouldn't be coined until a few years later. The concept came before the name. The rocks suggested an entire molten world before anyone had a word for it. Now, here is what happens as an ocean of molten rock slowly cools. It crystallizes. Different minerals freeze out of the melt at different times, like ingredients separating in a cooling broth. The lightest, frothiest material floats to the top and forms the crust. Denser material sinks and builds the mantle below. And the very last material to solidify the dregs at the bottom of the cup is rich in titanium. It forms that dense, titanium-bearing mineral we met earlier, ilmenite. Ilmenite has a problem. It is heavy, incredibly heavy. So once it finally solidifies near the top of the mantle, it doesn't want to stay there. It is denser than the rock beneath it, and so, slowly, it begins to sink. It sinks down through the mantle, deeper and deeper, falling toward the heart of the moon, toward the boundary between the cold mantle and the hot metal core. And this is where the picture suddenly comes alive. When that dense, titanium-rich ilmenite reaches the bottom of the mantle and piles up against the core, the heat pouring out of the core has somewhere new to go. Heat transfers across that core mantle boundary, pushes the ilmenite right up to its melting point, and sharpens the temperature difference across that boundary into a knife's edge. A sharp temperature difference is exactly what a dynamo feeds on. It drives convection-violent churning in the liquid metal of the core. And stronger churning means a stronger magnetic field. So here is the mechanism, finally, in plain language. The titanium-rich material sinks to the bottom. It melts at the core. That melting cranks up the churning in the core like throwing fuel on a fire. And for a brief, furious window, the moon's undersized core roars to life and generates a magnetic field far stronger than it should ever have been able to produce. The titanium didn't just mark the strong magnetism, the titanium caused it. That is why the rocks the astronauts brought back were both impossibly magnetic and unusually full of titanium. The two were never separate puzzles. They were the same event, recorded twice. And now I want you to notice one small detail, almost in passing. The rocks that carry this record, these dark, titanium-heavy basalts, only reach the surface as flows of lava that spread out across the lowlands and froze into wide, flat, dark plains. Flat, dark, smooth. Hold that thought. It's going to matter more than anything else in this story. There's still a piece missing. If the moon could generate a field stronger than Earth's, why don't we see that strength everywhere? Why is only about half the relevant sample collection screaming, while the rest is quiet? The answer is the strangest and most beautiful part of the whole story. The strong field was never the moon's normal state. The melting of that titanium-rich material at the core mantle boundary didn't last. It couldn't. The heat flux that drove it was only raised for very brief windows of time, and the moment the melting eased, the dynamo dropped back down to the weak field that the moon's small core could actually sustain. So the Oxford team's conclusion was this. For the overwhelming majority of the moon's history, its magnetic field was weak, which is exactly what dynamo theory says a core that size should produce. But every so often, for incredibly short bursts, the field flared to extraordinary strength. And when they say short, they mean it. These strong field episodes lasted no more than 5,000 years, possibly as little as a few decades. A few decades. On a world that is billions of years old, the moon didn't hum with a steady magnetic field. It had a heartbeat. Long, quiet stretches of weakness, punctuated by sudden, violent pulses of magnetism that came and went in a geological instant, and then fell silent again for hundreds of millions of years. Both camps in that decades-long argument had been right all along. The rocks really did record a field stronger than Earth's, and the physics really was correct that the moon's core should mostly be weak. The strong field and the weak field were both true. They just happened at different moments, and we had been arguing about which one was real when the answer was both. Now ask the obvious question. If these powerful pulses were so rare, lasting only a few thousand years out of billions, how on earth did the Apollo astronauts manage to bring home rock after rock that recorded them? The odds should have been almost nothing. By the mechanism itself, only about 2 in every 1,000 Apollo samples should have caught one of these rare magnetic surges. The real figure was roughly half. Half, instead of 2 in 1,000. That is not a small disagreement. That is the entire mystery, restated. The Apollo samples weren't just magnetic, they were magnetic far more often than random chance could ever allow. And the explanation for that, the final turn of the key, is the quietest, most human thing in the whole story. The Apollo missions didn't land just anywhere. They landed where it was safe. And the safest places to land were flat, smooth, easy ground for a fragile spacecraft to set down on without tipping over. And those flat, smooth plains were made of exactly one thing: the dark, titanium-rich basalt that floods up only during the brief windows when the heat flux is high and the dynamo is roaring. Do you see it now? The astronauts walked out onto the one type of terrain that is built almost entirely from the rare, supercharged moments. They filled their bags with the exception and carried it home as if it were the rule. For 50 years, we looked at those rocks and concluded that the moon's magnetic field had been strong for vast stretches of its history for something like 500 million years. It hadn't. We had simply sampled the lightning and mistaken it for the weather. This is what was buried. Not by NASA, not by anyone. The truth was buried by the landscape itself, by the simple fact that the easiest places to land happened to be the rarest places to read. The bias was baked into the ground. One of the Oxford co-authors, John Wade, put it in a way that lands hard. Imagine, he said, that aliens came to explore the Earth, and they only ever landed 6 times, and they deliberately chose flat ground every single time. They would walk away with a wildly distorted picture of our entire planet, convinced of things that simply weren't true, and never even know what they'd missed. If the Apollo missions had landed somewhere else, the team noted, we might have concluded the moon only ever had a weak field, and missed this whole violent, flickering chapter of its history entirely. We didn't find the truth because we were thorough. We found it because, half a century later, someone finally asked what the rocks were made of and realized we'd been standing in the wrong spot the whole time. Once you understand the magnetism, a much larger and more unsettling idea creeps in. If we got something this big, this wrong, just because of where we landed, what else is the moon hiding from us in plain sight? As it turns out, quite a lot. Consider the far side, the side we never see from Earth. In 1998, an orbiting spacecraft called Lunar Prospector swept the moon with a gamma-ray spectrometer, an instrument that can read the chemistry of the surface from above, and it found a spot on the far side that made no sense. It was glowing with thorium. Thorium is a radioactive metal, and this region, tucked between 2 craters called Compton and Belkovich, was packed with it. The thorium concentration there reaches around 5.3 micrograms per gram, while the surrounding lunar highlands carry somewhere between 0 and 2. For comparison, the Earth's crust sits at only about 0.06 of a microgram per gram. This single spot on the far side of the moon was blazing with radioactive material in a way that nothing around it could explain. Years later, a planetary scientist named Matt Siegler set out to understand it. His team did something clever. They used microwave instruments, including data from China's Chang'e orbiters, alongside NASA's Lunar Reconnaissance Orbiter and Lunar Prospector, and India's Chandrayaan mission to see beneath the surface. Infrared only reads the skin of a world. Microwaves can sense the temperature several meters down, and what they found beneath that thorium hotspot was heat. The ground there is producing roughly 20 times more heat than the background moon around it. Where the typical lunar highlands leak something like 5 to 10 milliwatts of heat per square meter, this one spot was running as high as 180. To feel how strange that is, line it up against the Apollo measurements. When the astronauts measured the heat flowing out of the ground at their landing sites, they got something like 15 to 20 milliwatts per square meter, already a little warm. Because they happened to be near the moon's radioactive near-side region. This far-side spot is running 10 times hotter than that, and roughly 20 times hotter than the quiet highlands. And here's the eerie part. You would never feel it standing on top of it. The surface there is still bitterly cold, around 80 Kelvin in the lunar night, far colder than anywhere on Earth. The heat is all underground. Walk across it and you'd sense nothing. Drill down just a few meters and the rock grows tens of degrees warmer beneath your boots. The moon keeps this furnace banked below a frozen lid, invisible from the surface, betraying itself only to an instrument tuned to see beneath the skin. The best explanation for all that buried heat was a body of granite. Now, that might not sound dramatic. We have granite all over the Earth. People put it on their kitchen counters. But here's the thing, and this is the part that genuinely unsettles geologists. On Earth, you make granite using two ingredients the moon doesn't have: liquid water and plate tectonics. You take ocean crust, drag it down into the planet, soak it, melt it, and remelt it, over and over, until what rises back up is granite. The moon has no plate tectonics. It has almost no water. By every textbook rule, it should not be able to make granite. And yet, hidden beneath the far side is a granite body, what geologists call a batholith, estimated at around 50 kilometers across and 20 kilometers deep. To put that in human terms, a batholith is the frozen root of an ancient volcanic system. The famous granite cliffs of Yosemite, El Capitan, and Half Dome are the eroded remains of one. There is something like that buried on the far side of the moon. The scientist who found it, Matt Siegler, by his own account wasn't even looking for it. He had set out to map the moon's underground heat, and the granite revealed itself in the data. He turned out to be ideally placed to recognize it. To his wife, Rita Economos, happens to be a geochemist who studies exactly this kind of rock, and the two of them pieced the discovery together. A husband and wife team reading the chemistry of the far side of the moon, and the strangeness compounds when you look closely. Most volcanoes on the moon are gentle, with slopes shallower than 7 degrees, built from runny lava that spreads out flat. This far side complex has slopes reaching as steep as 25 degrees, the signature of thick, sticky, viscous lava, the kind that builds steep domes rather than flat plains. The site is studded with them. Small bulges the researchers nicknamed Little Dome, Middle Dome, Big Dome, frozen blisters of an eruption that has been silent for billions of years. So how do you make granite on a dry, tectonically dead world? Nobody is certain, and that honesty matters. One idea is that this pocket of the early moon was simply unusually wet, letting the rock melt at lower temperatures. Another is decompression material from deep down, rising and melting as the pressure drops. But the most haunting possibility is that the granite made itself. Each time you melt this kind of rock, it concentrates more uranium and thorium radioactive elements that generate heat. Concentrate enough of them, and the rock can grow hot enough to remelt on its own, again and again, like a slow, natural nuclear reactor buried in the crust, cooking itself over millions of years. We don't know which answer is right. We may not for a long time. What we do know is how rare this is. Only about 10 silica-rich features like this are known on the entire moon, against a surface where roughly 16% is covered in ordinary basalt. The Apollo 12 crew once found a few grains of granite on the near-side grains, the size of specks. This is a body 50 kilometers wide. It is, again, the same shape of mystery as the magnetism, a thing the rules say shouldn't exist, sitting quietly on the side of the moon we can't see. And there's a deeper riddle wrapped around it, the strange split between the moon's two faces. The near side, the side we see, is patched with dark volcanic plains and loaded with radioactive, heat-producing material. The far side is older, quieter, and its crust is nearly twice as thick. For some reason we still don't understand. Almost all of that heat-producing material pooled on the near side, the side facing us, as if the moon had been shaken like one of those toys with a bubble inside, and the bubble had drifted to one face and stuck there. This lonely granite complex is the great exception, the one major outpost of that material stranded on the wrong side. Why it ended up there, nobody can yet say. The moon isn't only hiding ancient secrets either, it's still moving. A scientist named Tom Waters went back to the seismometers the Apollo astronauts had left behind, instruments placed on the surface between 1969 and 1971, and reanalyzed moonquakes they recorded. 4 of those instruments captured 28 shallow moonquakes through 1977, some of them as strong as 5 on the Richter scale. That's a real quake. You would feel that. And the cause is almost poetic. The moon is shrinking. As its still warm interior slowly cools, the whole world contracts, like a grape drying into a raisin, and its brittle crust cracks and buckles. Where it breaks, one slab of crust is shoved up and over another, leaving long, cliff-like steps across the landscape that geologists call lobate scarps. Over just the past several 100 million years, the moon has shrunk by about 50 meters, and the Lunar Reconnaissance Orbiter has now photographed more than 3,500 of these young faults wrinkling the surface. Here's the detail that makes it real. One of these scarps, the Lee-Lincoln Fault, runs straight through the Taurus-Littrow Valley, the valley where the final Apollo crew landed. The astronauts drove their rover right over the face of that cliff. They photographed boulders that had tumbled down it, and the fresh tracks those boulders left behind, the fingerprints of recent shaking. They were standing, without knowing it, on the living evidence that the moon was still quietly tearing at its own seams. When Waters lined up the moonquakes against the faults, 8 of the quakes fell within 30 kilometers of one, and 6 of those 8 struck when the moon was stretched farthest from Earth by tidal pull. He ran 10,000 simulations to test for coincidence. The odds came back at around 4%. And even the moon's most violent chapter is being rewritten again, from the far side, using lunar soil returned by China's Chang'e 6 mission, which launched in 2024 and carried back nearly 2 kilograms of material from the far side. Researchers dated one of the great far side impact basins from just 3.5 grams of that dust by reading tiny impact-melted fragments like geological clocks. They fixed the formation of the Apollo basin at around 4.16 billion years ago, pushing the start of the moon's era of heaviest bombardment back by at least 100 million years. A separate study of the same haul dated the enormous South Pole Aitken Basin, which sprawls across roughly a quarter of the entire moon and is the largest known impact crater in the solar system, to around 4.25 billion years. 3.5 grams of soil, quietly redrawing the timeline of how our moon was forged. The moon we were taught about was dead, a frozen, finished relic. The moon the data describes is none of those things. It is magnetized in flickers, salted with rock that shouldn't exist, scarred by a quarter-moon-wide wound, older than almost anything, and still trembling, gently, beneath our feet. Step back from all of it, and a single thread ties these mysteries together. It isn't a thread about the moon, it's a thread about us, and about how little of it we have actually touched. We have walked on the moon, we have driven across it, drilled into it, and carried pieces of it home. And it is easy to feel, because of that we know it. But the truth is that we have only ever sampled a handful of spots, almost all of them clustered on the near side, almost all of them chosen because the ground was flat and the landing was safe. A whole world, read from 6 landing sites on the easy terrain. Think again about John Wade's image of aliens visiting Earth 6 times, always touching down on flat ground. They might never find a mountain, never find an ocean trench, never find a glacier, or a desert, or a volcano. They would write a confident history of our entire planet, and almost all of it would be wrong, and the deepest problem is that they'd have no way of knowing it was wrong. The gaps wouldn't look like gaps, they'd look like the whole picture. That is the position we have been in with the moon. The strong magnetic field, the buried granite, the shrinking crust, none of these were truly hidden. They were simply outside the small circle of places we'd looked, or buried inside data we hadn't learned to read yet. The moon never kept a single secret on purpose. It just waited, patiently, for us to widen the circle. There's a way scientists describe this limitation that captures it better than anything. For the entire history of our species, when it came to understanding how a rocky world is built and how it lives and dies, we were like a doctor with a single patient. One Earth, one example. And you can only learn so much about how a body works, how it ages, how it breaks, what's normal, and what's rare if you have only ever examined one. The moon is our second patient. Mars will be a third. Every world we can actually touch and sample turns a guess into a comparison, and a comparison into understanding. Which is exactly why getting that second patient wrong for 50 years over something as fundamental as its magnetic field should make us humble about how much of the rest we still have backwards. And to be honest about where the science actually stands, this is not a closed case. It rarely is. Even the magnetism mechanism, the sinking titanium, the melting at the core, the heartbeat of strong fields remains a hypothesis that other researchers are still testing. One specialist in planetary dynamos, John Tarduno at the University of Rochester, called the idea intriguing and certainly worth further consideration, while making clear he isn't yet convinced that heat from the core alone could flip the moon's dynamo on and off like that. He thinks it should drive new simulations and new modeling. In other words, it's a compelling answer, but the moon hasn't finished being questioned. That's not a weakness in the story. That is the story. Every answer the moon gives us arrives holding the next question. And for the first time in half a century, we are about to widen the circle. The Artemis missions now being prepared aim to send people back to the lunar surface, and crucially, to ground we have never sampled before, near the South Pole. The same Oxford team that solved the magnetism puzzle has said plainly that these new missions are the chance to test their idea, to go somewhere other than the flat, titanium-rich plains, and see whether the rocks there tell the weak field story the physics predicts. China's Chang'e program is already pulling samples from the one place Apollo never reached the far side. The Chang'e 6 mission, which launched in 2024, brought back nearly 2 kilograms of material from the lunar far side. And from just 3.5 grams of that soil, researchers were able to date one of the great far side impact basins, the Apollo Basin, to around 4.16 billion years ago, pushing back our timeline for the moon's most violent era by at least 100 million years. 3.5 grams of dust, rewriting 100 million years of history. Further missions are planned to keep going, deeper into the places we've never stood. And we are beginning to listen to the moon again too. The only seismic data we have ever had came from those few Apollo instruments, clustered on the near side, switched off since the 1970s. New seismometers are being prepared to return, including a package built to listen from the far side, the one hemisphere from which we have never heard a single moonquake. For half a century, our entire picture of the moon's trembling interior has rested on a handful of microphones in one small neighborhood. We are finally about to hear the rest of the room. Each one of them is, in a sense, the same correction. Each one is us, finally walking off the flat ground. So think about that rock again. The small, dark, heavy one, sitting in its drawer in Texas, holding a magnetic field stronger than the Earth's, recorded during a pulse that lasted maybe a few decades on a world billions of years old. We pulled it off the moon. We carried it across space, we locked it in a clean room, and then we misread it for 50 years, not because anyone hid the truth, but because we never thought to ask what it was made of, and we never realized we'd only been standing in the one place that lied to us. The moon did not bury its secrets from us. We buried them ourselves, under the comfortable certainty that a few rocks from a few flat places were enough to know an entire world. And the most humbling part isn't how much we got wrong. It's the quiet thing underneath it that our closest neighbor, the one world we have actually held in our hands, The bright, familiar face we have looked up at for every night of human history is still, after everything, a stranger. We are only just beginning to learn how to read it. And it has been waiting, all this time, with the answers sitting in plain sight, bright as a thorium glow on the far side, patient as a fault line, written into a rock we have been holding the whole time and have only now begun to understand.